Assalamu alaikum, Bismillahirrahmanirrahim. Today we will start lecture number 11 and 12 of 6-week lecture. We have covered one third of our subject. So before starting this subject, I just want to address some of problems which we are facing in our live session and also in lectures. The first problem, the most important problem which we are facing, it's attendance. The two extension which our management has told us, I use that extension and make attendance, but still there are some bugs. Some of the students attendance has not been recorded by this extension, so I just went back to the chat history and searched each and every student name which are calling their attendance has been missed. So it's a very it gives me very tough time to me, and it takes around 3 to 4 hours. And after that I was able to sort out the tables and can assist with the conditional formatting. So now it becomes easy for me to filter out that names and make attendance by putting conditional marking command in Excel files. So in future, if you write your roll number, I can easily mark your attendance. But still, in today live session, some of the students are claiming that they are not able to write their roll numbers. So to address that, I just put Google form in the end of the live session, and even on that, some of students complaining that they are not getting permission of that. So I think that will be some problem by their end. In the Google form I never face this kind of problem, but anyhow I will check in next session before the class, so this kind of permission problem will not assist. So in the next class you just mark your attendance twice by putting your roll number in the chat history as well as by entering the Google form. So inshallah in future this problem will not come in our future live session. Of course this online teaching is challenge for me and for you people also. It cannot be replaced by the physical teaching that we are doing in our university life. I just went all the students to the labs and show their physical machines. So it is quite interesting. That subject is basically based on the physical things, physical machinery, the process inside them. So by watching and seeing that machines, it will be very interesting for the students, as I've experienced in the last 2 batches of electrical, electronics, urban engineering. But still I'm trying my best to put pictures as well animation to make you understand the process behind the actual or practical, and I will also try to give you practical exposure of that things, not only theory thing. Anyway, the one of the complaint or students are demanding PDF lecture. So in future I will provide, but just right now after this lecture I will share PDF files of all my lectures till lecture number 10. So you can download it and make a copy of it. You can also have a copy of it. Another thing which I want to address, that right now the management has made decision to record all the lecture views, record the attendance of lecture view session. So don't get the copy of lecture from anyone else. Watch that video by yourself. And this logs has been maintaining by Google Cloud, and they are providing us their logs, and we get attendance of your lecture views. Okay, so it is compulsory, you have to watch that lecture by your official cloud ID. Remember that. Now even if still before starting this lecture, I just want to address one mistake I have done in the numerical. in the previous numerical in lecture 7-8. The students, yes, this is the mistake that I have done. No, I think yes. In lecture 7-8 I just solve the numerical in the correct manner and all the values are correct, but just replace 2 v2 v1 in opposite direction. Yes, in example number 2.1, here when we are finding out the pressure values P2, the equation is P2 v2 power n is equal to P1 v1 n, and when we have to find out P2, v2 goes to into the denominator and v1 in the numerator. So I just write v2 in place of v1. In denominator I just write v1 and in numerator I write value of v2, but in the calculator I solve in the correct manner. That's why I get this correct answer, and we successfully calculated the work, that is positive 17.6. It is positive 17.6. Negatives I just mark in the explanation, and you can see in the video, so it's not a mistake. So move towards our lecture 11-12. Today we will start with the one small topic that is related to the ideal gas equation, and then we will solve one numerical, the last numerical of closed system, and after that we will study open system and then some 1 to 2 numerical over there. Then we just move towards the refrigeration cycle. Students also asking for the practice question, so I didn't give practice question because recently we get the mail that the sessional marks are in the process of deciding by the higher authority, so don't give any kind of assignment which can utilize for the sessional marks. So that's why I didn't give you any assignments or practice question, etc. But you can solve by your from the book. I just shared the book Sangel in the books and reference folder, but it's by your for your own practice you can sort out some numerical related to the lecture numerical, and so you can solve by your own. I'm not recommended by right now due to the management policy. So let's move towards our lecture. Before doing this numerical, we will use the ideal gas equation is PV is equal to MRT, but in pre-engineering you studied this equation as a PV is equal to nRT. So here is a difference why we are using PV is equal to MRT and not nRT. We drive this equation in the masses. Basically when we talking about the equation of the state, any equation that relates to pressure, temperature, specific volume of a substance is called equation of state. We already studied solved the numerical of the PV is equal to N is equal to C polytropic process. This is also a compression or expansion process. It is also equation of state on that time, but joining all the properties along in a single equation, that is called the equation of state. The simplest and the best known equation of the state for the substance is the gas phase is the ideal gas equation state. PV is equal to nRT, P is equal to pressure, P is pressure, V is volume, N is the amount of the gas, whether it is written in the number of moles or in the mass. Actually in the below equation it is written in the amount of gas in M, that is in kgs. The universal R is universal gas constant and T is temperature. It is ideal gas equation and it is used for ideal gas only. But if we convert this equation for a particular gas, like for nitrogen, for air or any other gas, we have to convert this equation into PV is equal to MRT, where we take this we take the constant R, not universal, but of a particular gas. For air R is different, for nitrogen it is different, and we will take this gas constant from the table, like steam table A4 A5, and we will see in the SI table of thermodynamics the value of R2. So now how it is convert this PV is equal to nRT into PV is equal to mRT. It is simple. The gas constant, it is universal gas constant, and it is gas constant for any particular gas. So it is by a simple formula, R is equal to universal gas constant divided by molecular mass, and N is equal to N is for the formula of N is number of moles is mass of a substance divided by mass of 1 mole. Okay, so now we are relating this just we are putting the formula of N and R and form N is equal to mRT, like PV is equal to N, and for the N we we can write this like this, and here it is RU. So RU is R multiplied by capital M and T. So now this, the mm will cancel, and the equation becomes PV is equal to mRT, like this. So converting the ideal gas equation to the particular equation of state for a particular gas, it is called, or it is written like PV is equal to mRT. This is a short derivation of it. So we move on. For the remaining numericals, we will either for the closed system or open system, we will use this equation PV is equal to mRT, and we will take this R value from the table of a particular gas, whether it is air, whether it is steam, whether it is any other substance like nitrogen, etc. Where the R is the constant of proportionality is called gas constant, where R is the universal gas constant, and M is the molar mass. So let's move on towards our numerical. This is example, this is not example, this is actually question 4.63 from the book of Sangel. You can get this question from the shared book. An insulated piston cylinder device contains 100 liter. This is mass of air at 400 kilopascal and 25 degrees centigrade. A paddle wheel within the cylinder rotates until 15 kilojoules of work is done on the air while pressure is held constant. Determine the final temperature of air. Neglect any energy stored in the paddle of wheel. So it's a very simple numerical. The paddle wheel rotates, the paddle wheel rotates. When the paddle wheel rotates, this fan is giving internal energy to their gas inside the cylinder, and due to this the temperature will increase. If we kept constant the pressure, if the pressure is kept constant, then any energy provided to the system, it will increase the temperature of the air. So this numerical, we have to solve this numerical. So we apply the same equation that we have studied for the closed system, that delta E is equal to Q minus W. Let's move towards S node. So this is previous numerical. I just move on the new one. Yes. So we apply the same formula, delta E is equal to Q minus W, and delta E is the sum of kinetic plus potential plus internal energy. This will goes to 0, this will goes to 0, is equal to Q minus W. So I'm doing this numerical directly, but when you are solving this in the paper, you have to write data separately, so it will ease the numerical. Right now we are solving, so we can directly solve the solution part only. So delta E is equal to simple U2 minus U1 is equal to Q minus, we have two work over here. Like in previous numerical, we have two work. One is the pressure volume work, and another one is heat energy that is providing to you by the directly electricity. Now here we have the mechanical power of paddle wheel. So we have two energy. A paddle wheel within the cylinder is rotated, so we are providing paddle wheel work 15 kilojoules, and another work which is converting it is the pressure volume work. If we cap that pressure constant, the piston will move forward, so it produce some work. So it is pressure volume work. So now we split the work into two. Sorry, we have to move towards here. So one is the, and by the notation in this process, heat is leaving the system, or so it is from the equation. If when the q is not given, you can get the idea from this point. It is an insulated piston cylinder device, means it is an isolated system. In isolated system, the heat is not transferring from system to bond, so there will be no heat transfer, so q will be 0 in this state. So the q will be 0, this is 0, and the work is split into two parts. One, it is work by the wheel, and another one is the pressure volume work. So work is adding to the system, so anything added to the system by the sign of convention, it is opposite to the heat transfer. So we apply this the negative sign. Paddle wheel, we write this with P, paddle wheel, work of paddle wheel, it is the sign notation with negative sign. And pressure volume work is done by the system. It is work done by the system. It so the sign convention will be opposite to it. So mechanical power we have Wm and negative. So by opening this will be 0. This minus become plus paddle wheel power, and this become minus, and it is the work pressure delta V. Here again I don't want to explain again that why we are using P delta V here, nor integration P dV, simply to simplify this numerical. For accurate work, we must or we should use integral P dV, where we know the process, exact process of, and have the known value of n, etc. So right now we have to convert in the enthalpy. So that's why we take this P delta V work, the work basic formula P delta V, and we can it is in the negative. When it goes to that point, it becomes positive, and we open also P V2 minus V1. Sorry, it should be the next step, not here, u2 minus u1. And in the next step, when we move like this, we can write this with v2 minus v1. We open delta v over here, okay, and here we the paddle wheel power. Then we are rearranged like this, u2 plus pv2 in this, and take this negative sign common, and u1, and when we take negative sign common, so it becomes pv1. We multiply p with v2 and v1. Now it is this. We have ample space over here, so we can split this space like this, and we can write over here. Now this becomes internal energy plus pressure volume work is basically enthalpy. It is a combination of internal plus pressure volume work, so it is becomes H1, and this is so H2 minus H1. Again we can write this with the short form, M H2 minus H1 is equal to work P. So like in the steam we have enthalpy at a constant pressure. In this example we have a working fluid here, so we also have a table of air which can give us the value of enthalpy at constant pressure, and at this numerical we have a pressure of 400 kilopascal. So it is all we should write data over here, so we cannot shift the question again and again. So I just recommend you to start with the data. So we will find out H1 at 400 kilopascal, and by this formula we get the value of H2. So we can arrange this like this. M goes to here, and H2 minus H, the bracket become open, so H2 minus H1 here, so when it goes toward there, so it becomes H1. Now H2, now we just need to find out we know the value of WP is 15 kilojoules, mass 100 liters, so we can convert mass into by weight 1, if we can by the density simply. So now we need to find out the mass of the air, and we can get the value of H1 from the SI table of thermodynamics. So to calculate the mass, we applied the same equation of the state PV is equal to MRT. So we mark this equation to equation 1 and recall again when we required. Now we will solve for the mass, and for solving mass we apply the equation of state PV is equal to MRT. If we call it state from state 1 to 2, and we have known value of state 1, so we can write this P1 V1 is equal to MRT1. Mass is constant, mass is not going anywhere, it is isolated system. So now the mass formula becomes P1 V1 is equal to RT1. So P1 is 400 kilopascal, volume is 100 liter, so we can use meter cube. So 1000 liter is 1 meter cube, so 100 liter becomes 0.1. Simply divide 100 by 1000, you get the answer 0.1 meter cube. And we take R value from the table, and T1 the numerical tell us the temperature, but we use the temperature in the Kelvin. It is given 25 degrees centigrade, so 25 plus 273, it's 290 Kelvin. So now we have to find out the value of R. So we move towards SI table. From SI table you can go to table A2. Please don't need to memorize these values in the paper, you will provided this tables. Okay, so here we gas air, and the value of air R is 0.2870. You will see that from the different gases, from the different element, you get different R value. So that's why we are using gas equation state of universe, not using R universal gas constant but gas constant. So again we will move towards 0.2 now of the zone. So we can move towards, so we can take sorry, mass is constant, so it is only M is equal to P1 is how much the P, 400 kilopascal. 400, we are applying this K form. Okay, and volume is 0.1 meter cube. As told you, 100 liter is 0.1 meter cube. R value 0.2870. Now you have a question, why we are using kilopascal over here? Because it will cancel out with the R value. R value is also in the kilojoules per kg, so kk will be cancelled out and we get the answer in the kgs form. So if we write the units, you can write the unit kilopascal and kilojoules per kg, so kg cut cancel out over here. So to simplify, we are not writing the units over here. And the temperature is in the Kelvin 298. 25 degrees centigrade is 298. So we get the value of the mass 0.468 kg, 0.46 kg. Then recalling equation number 1, that is H2 is equal to Wp upon m plus H1. Wp, what is pedal power is 15 kilojoules. So 15 kilojoules divided by mass, that is 0.468 plus H1, and H1 comes from, we can write here at 400 kilopascal. H1 is equal to, now we have to find out H1 at 400 kilopascal at constant pressure. The value of H, so it is steam table. Now we have to move on their refrigerant temp table. We have to find out table of, yes, ideal gas properties of air. So now at pressure, like no, we also have a temperature available, so we get the value of H1 by the T1. So we have a temperature like 298 is close to 298. Yes, we can the value of 298, and the value of H is also the same 298.18. So we can take this property from table A17. We can write over here, not from the pressure table. We have a at 298 degree centigrade, H1 is also 298.1 from table A17. Yeah, right, from table A17. Yes. So now H1 can be written directly over here, that is 298.12, I think it is 12. Now solving this, we get 329, sorry, H2 is 330. By solving this 290, it is simply 32.05, 2.05 plus 298.12. The answer will be 330 kilojoules per kg. Kilojoules per kg. So we are over time. We have a class 43 minutes, so we have to end this. Now the question becomes very easy. We get the H2 value, and the from same table A17 at 330 at H is equal to 330. The T2 is 330. We have the same from 330 330 enthalpy giving the same temperature 330 Kelvin. Oh sorry, it is in the Kelvin. It is showing the value of T Kelvin. And if we convert 330 minus 273, it is T2 is 57 degree centigrade. So this is how we can solve the numerical from the same procedure. Now stay safe. We will meet in the next live session in the next class, inshallah. Till then, Khuda Hafiz and take care.